Swayam Prabha. Digital India. Educated India.
It is our pleasure to once again welcome Professor Arvind Rameshwar to our session today. We are already familiar with his engaging and insightful lectures, and we are truly delighted to have him back with us. We are grateful for your time and eagerly look forward to learning from you once again, sir. Please join me in giving a warm welcome to him for today's lecture.
Okay, so welcome back, and pardon me if I'm going to go a little over time today. So the agenda is like this. We'll go back to whatever we were doing last time, take a short recap, go to something new, and then the last 5 minutes or so I want to just talk to you about what you can do going forward and so on. Okay. It's just a freewheeling discussion. Okay. So I intended being prepared for this lecture, but what happened was I changed my bag. So the notes that were there in the previous bag is not there in this bag, so I'm going impromptu. So let's just see. What do we recall about the compression problem? So we had information, we had messages that we wanted to compress, remember, right? So we started off with something called Zipf's law. And what did this law say? Yeah, in a picture it looks like this. So suppose you have, so this is a picture of Moby Dick or Pride and Prejudice or whatever. And these are the words that occur in that novel. Okay, so these are words. And what you see on the y-axis are frequencies of these words, right? Frequencies. And if you have attended RSIC for long enough, you will start calling frequencies as probabilities. Thank you. So what does probability here mean? It means the number of times that word is occurring divided by the total number of words in that novel, right? And all that Zipf's law is saying is that, well, the probability doesn't look like this. It's not all uniform. Rather, it looks something like this. It's just a feature of natural text. What did we then say? We said that, okay, let's just work with some such distribution that occurs in nature. And the goal now is to compress this information. Right? So what does compression actually mean? It means that you have a large volume of information and somehow you want to condense all of it into as few symbols of representation as possible. So the picture you should have in mind is something like this. This here is Moby Dick, the novel. Okay? 900 pages long. But what is the amount of information that it truly contains? It contains much, much less. Okay? And this is really the goal of compression. Okay? You want to condense all the information that is present in a certain novel or in a certain data set into as small a representation as possible, primarily for storage purposes. So storage is good here. But this kind of sounds strange, right? Because there are so many words in this novel. What do I even mean by representing the essence of the novel in as few symbols as possible? So that actually got us back to this picture where we said, you know, most of the words occur with very, very low probability. Okay? There are a lot of words that occur very, very infrequently, and those words don't really contribute much information as far as we are concerned. Right? So we don't need to go about assigning a lot of representation to them or caring too much about their representation links. So what we really care about are these words. Okay? And so long as we represent these words as succinctly as possible, we are going to get as short a representation of this novel as possible. Great. So, whenever we talk about compression, the standard example is what is called the .zip format. So, have you worked with zip files? So, zip is essentially a way of compressing files down to minimal size. Okay. You would have also seen if you use a Mac .tar, .gz, and so on. And all the mechanisms that are at play here are precisely the mechanisms that we covered last time. So you may see a lot of math in all of these lectures, and then you may be wondering, what are these guys talking about? How is this translating into the real world? The fact is that all of these algorithms or all of these software packages that you see in your systems make use of the very same algorithms that we are talking to you about in class. Right? So, for example, in your CBSE portal, which is famously buggy, you will be asked to upload an image of yourself, right? So, your image, I mean, nowadays everybody takes high quality images. Who takes like, so image size roughly nowadays is about 10 MB, okay? If you want to look good in an image, you better take it at least at 10 MB, otherwise you're looking silly. But then CBSE says, you know what, I can't support so much information and all. I have only so much storage space with me in Delhi. Okay, all my servers are in Delhi. My servers can only hold so much information per individual. And he says something absolutely ridiculous like 400 KB or something. Okay. This is wild. How much is the order of magnitude of difference here? Huh? So 400 KB is 400 into 10 to the 3, that's 4 into 10 to the 5. This is 10 into 10 to the 6, that's 10 to the 7. So that's order of magnitude 100 times. 100 times you need to compress, you need to do something to your image in order to get CBSE to even accept that you are a 11th grade individual. Okay. But it is what it is. The Indian government works that way. So we need to go about doing this, right? So all the mechanisms that are at play here are precisely the mechanisms that you saw last time. So these are the compression algorithms that you see in action on such portals. But they also do something more. They also do something called downsampling, but I'm not going to talk about that this time. Okay. So goal is clear. Goal is we want to compress information down to as less of a representation as possible. Huh? And what did we see at the end of last class? We saw something that had to do with quantities that look like this. So what was this? Can you remind me? What is this? Optimal average length. Okay. So I have such a distribution. I am assigning certain code words to every word. So for example, suppose this most frequently occurring word is A. I assign say 0 to A and so on. Okay, and then next most frequently occurring word is the, for example. I assign 1 0 to the. Going by our logic last time, we wanted prefix freeness. So we do something like this, and then we compute what is called the average representation. And in a certain sense, that happens to be the optimal average representation length. Okay, so you can't do better than that in some sense. And we kind of convinced ourselves of this. Okay. So this guy here is the optimal average representation length in some sense. Optimal average representation length, but suppose I were to read n words of Moby Dick. Okay? Not with just one word of Moby Dick, with n words taken as a string. So for example, for that recurring, so suppose you see to be or not to be. So this is 1, 2, 3, 4, 5, 6. 6 words of representation, 6 words, so n is 6 here. And suppose 2 is assigned some value, I'm just going, okay, I'm just saying something. Something like this, okay. Then n here is 6, and ln star happens to be how much? It's just the sum of these lengths. So 2 plus 3 plus 3 plus 5 plus something, okay. So that is my Ln star, and I am dividing by n itself. N is 6 here. So we started looking at this quantity, and then we said, you know what, it's actually amazing that this quantity is a constant in the limit. Okay. So let us parse what this means. So suppose I were to represent, suppose Moby Dick were an infinitely long novel, okay, like a very, very long novel, then the amount of bits of representation that I will need is only so much. But how long is Moby Dick actually as a novel? It is n words long. Okay? So the novel has n words, but I am representing it using n times h of s number of bits. Importantly, this h of s value, whatever we saw last time, is smaller than 1. Okay? So that was the takeaway. Fine? So long as you have a nice enough distribution, nice enough frequency of these words, you can toy around with what this h of s value is and make it come down as much as possible so that you can represent this novel in as few bits of information as possible. Okay. For example, if h of s is half, then I am representing Moby Dick using just half the bits. Right? And in particular, for the CBSE website, you guys are so redundant that your h of s is actually 1 by 100. So we require only n over 100 number of pixels to represent you. Okay. So whatever your photographer does in Konica or whatever is just an overly redundant representation of your face. I just require a very, very downsampled version in order to know that it is you. So that's what is going on. Any questions about this? Yes, so the way you should see it is this. So h of s is some fundamental limit. Okay? H of s is like the speed of light. You cannot get better than h of s when you try to compress information. But what Huffman codes allow you to do is that they actually allow you to achieve h of s. Okay? So you can design a scheme, design a code book, so to speak, that gives you h of s on average. Right? Any questions? Okay, so in words, what is the takeaway? So the compression task that we saw is equivalent to removing redundancy. Right? Because we have a lot of redundant information in our videos, in our text and so on, and we want to strip our books and images and so on bare of this redundancy. But then there is a dual problem that requires one to actually add redundancy. And that is this problem that we will talk about today, which is the problem of standard communication. So when you enter the precincts of an electrical engineering department, people will start talking about coding. What they mean by coding is not computer programming, so that we call as programming. Coding is something else. Coding means designing a code book. Okay? So that's where the word code comes from. So if you hear the word coding in this department, we are referring to this. If you hear coding in the AI department, they are talking about something else. Okay. So we had this discussion some time back about where the word concentration comes from with a bunch of you guys. It's kind of wacky where these words come from, and they all that they do is confuse individuals. Okay. So for the moment, let us just stick to calling this coding because you heard it first from me. And then later on in your life, when you encounter coding in your AI courses, go tell your instructor that no, that's not what coding is, this word is. So let's go to this other problem called comps. And this problem is remarkably interesting. Okay? So and my intention is to present to you a kind of simple version of this problem so that you can take back the essence of it. So the essence is something like this. So this is me, okay? This is me. And this is my mother, okay, at home. And I want to tell my mother, and I want to signal to my mother whether I'm going to IIT today or not. Okay, that's my end game. She's all concerned, you're leaving today, where are you going to IIT? But I want to tell her yes or no. Okay, which is 0 or 1. One bit of information. Right? So yes is the same as 1 and no is the same as 0 for me. But let's make our life complicated, okay? So we are at IIT Madras, let's just screw with your minds. I am going to call 1 as -1 henceforth. And I am going to call 0 as 1. Okay? You will see why. So 1 from now onwards is -1, 0 is +1. Huh? Just to be clear, this represents a 0, this represents a 1. Okay? So I want to convey to her 0 or 1, or in other words, I want to convey to her -1 or 1. Okay? Because she knows I'm a crazy guy, so I'm calling -1 as 1 and 1 as 0. Okay? So I have this piece of information with me. It resides only in my head at the time of my waking up. Fine? Nobody else is privy to this information. But I want to get this piece of information across to my mother. She is sitting in some other room, okay, watching her phone or whatever, and I'm sitting somewhere else. And being the lazy guy that I am, I don't go to her and tell her. Okay? So what I do, this is a house, so you have mirrors, you have a random cupboard, you have some other artifacts, okay, so some other random things, dining table, something. And I yell my answer out to her. That's what I do. This is what all of us do, right? Because we're super lazy. I say -1 or 1. I don't yell -1 or 1. It's an electrical engineer's house. So I have a small remote with me. She has a receiver of that remote. And if I press a certain button, she knows it is -1. If I press the other button, she knows it is +1. Okay? She has the receiver. But the problem with this remote is, it's a remote at the end of the day, and my mom is watching the telly, my father is watching something else. It's a pain. So my mom is getting all these kinds of signals from everywhere. So the signal that I transmit is first sent to my mirror, and then the mirror bounces off this signal. Then another part of my signal goes to the dining table and gets absorbed. Another part of the signal goes to the cupboard, and then the cupboard has some shiny reflective surface and it goes to my mom again. And likewise and so forth. Okay. Goes somewhere here, comes to my mom, or something else. So my mom has all of these varying pieces of information. So like this fellow, does he want to go to IIT or not? But I only transmit once, okay? I don't tell my mom twice, only once. My mom gets all of this information and she wants to put all of it together in order to understand what the hell it is that I'm saying. So let us think of a simple model for this communication setup. So this is a communication setup, right? I'm going to communicate with another person. So what is going on is this. So you attended Uday's talk, Uday Khankoche. So Uday would have predictably spoken about some electromagnetic fields, something. Did he? Okay, I don't know what he spoke about, but yeah. So what goes on at the end of the day is this. Whatever I transmit is an electromagnetic wave, right? And electromagnetic waves you guys would have read about in physics in some respect. They get reflected, they interfere, and so on, right? So let us look at a very simple model of how these electromagnetic waves behave. This is very, very simple. Every time my mom receives some random information which is somewhat biased towards whatever I sent. Okay? Let me be a bit more precise. So X is what I want to transmit, which is either a -1 or a 1. And this Z information is noise, okay, is what we call as noise. And this noise occurs in many ways. It occurs because of all of these random reflections, random absorptions. It occurs because there's a crow cawing somewhere else, and then that kind of interferes. It occurs because there is some solar rays which interfere with the signal from my transmitter and so on. Okay. So every time my mom receives X plus some Z, okay, on every path. And what is this Z? This Z is something that is either -1 or 1. Okay. Okay, let us just assume that my mom receives X plus Z, where Z is something in this interval. Okay. Z is some value like -0.5, plus 0.5, 0.2, -0.7 and so on. Okay. This is just some random thing. Is that okay? Not okay? Okay, not okay. So every path has noise attached to it. Okay. So this is X plus Z1. My mom receives X plus Z2 from this path. She receives X plus Z3 from this part, but unfortunately Z3 is cancelling my information out. Okay. So Z3 is like -X. All right. All on page. Yeah. Yeah. She has a look at all of these. So who asked? Sorry. Yeah. She has a look at all of these values. She can see the value itself, not just whether it is positive or negative. Okay. So what does my mom have? Mom has X plus Z1. She has X plus Z2. X plus Zn. I have X. And my mom wants to figure out what X is from all of this information. That's the name of the game. But my mom is smart, okay? So what she does is this. She constructs a new value from all this information that is present with her. Okay. She adds everything up, okay? And then she divides by square root of n. Okay. She divides by square root of n. It's a bit wacky, but then it's what happens in my house. Okay. So people divide by square root n all the time. So my mom just adds everything up that she receives, divides by square root of n, and then somehow magically she says, whatever I have is some very, very noisy version of whatever you sent. But you guys have seen this somewhere, this entire business of division by square root n. Sorry? Okay. Yeah, standard deviation comes somewhere. Standard deviation here I am actually assuming it is 1. But you have seen this form somewhere. In RSIC we have overloaded you with probability enough for you to tell me what this is in your sleep. Sorry? This is, yeah, ballpark. So, expressions of this kind are what you saw when Pranay spoke to you about the central limit theorem. You guys remember him telling you something like this? He was talking about pressure and molecules colliding against the surface, and then on average something happens which reduces something. And what Pranay told you at the end of the day was that what this expression looks like, right? It looks like X plus something, and this something is distributed according to what is called a Gaussian distribution or normal distribution. Okay? So I heard quite a bit of 1 by 2 pi business here. So what is this 1 by 2 pi? So let's look at this again. What does my mom have? My mom has just one value, this value. Okay? Mom has only this value. And with this information, she wants to guess what this value is. This is what actually goes on when you communicate via mobile phone and so on, right? Because you're picking up your phone and making a call, and the call goes to something called a base station. Okay? So this is like a tower that sits outside, that sits actually inside IIT Madras. And then this tower receives this information and then tries to send that information across to your receiver. Okay? So what is this 1 by 2 pi business? You guys were saying something. Yeah, I mean, can you tell me a little more in full? Like eta has something to do with whatever it is that you were saying. This is eta, by the way. Sorry? More or less. So let's see what this means. So you would have seen a curve of this kind. This is what is called the Gaussian distribution after Gauss. It's also called the normal distribution sometimes. Okay. But what is this actually? So is this eta itself? What is it? What is it? Huh? Speak up, can't you? Is it white? So what is the x-axis here? No, yeah, x-axis ranges from minus infinity to infinity, but what is the x-axis? Sir, I can't hear you guys. Huh? What signal? X. X is either minus 1 or 1. What is this? Okay, good. So this is what values eta can take. Okay. The x-axis are all the possible values of eta. What is the y-axis? We've been drawing plots like this in the hope that you guys understand. But okay, good, thanks. Yeah. So this is something like probability. Okay. This is, thankfully there are no math guys in the audience, but they'll crucify me. So it's something like the probability of eta. Something like. Okay. Why is this something like? It is because it's not really the probability, it's like the derivative of the probability, but then let's leave that for another thing. So what does all of this mean? It means that eta can take these values. Eta can take one of these values, and whatever you see on the y-axis is the probability with which eta occurs with that value. Fair enough? And that function is the 1 by 2 pi business that you were speaking about. Okay. I'm just going to write it here, but we are not going to use its exact form again. So what I've written here is 1 over square root of 2 pi. This x here is my way of writing e power. Okay. So this is 1 by square root 2 pi e power minus eta square by 2. Fancy something. Okay. The plot of this is this. And this is actually a probability plot in some sense. Okay. So let's get back to this question. My mom receives x plus eta. Huh? Eta I am saying are these values. This is the probability of eta. In other words, my mom receives this particular value of eta with this much probability. She receives this particular value of eta with this much probability. This particular value of eta with this much probability. Eta is a random variable. It's completely random. it occurs with a certain probability, the plot for which you see here. This plot is symmetric, it's cute, it's nice, all that. Okay. Fine. So now what is, we have this kind of a plot, this is 0. So what does x plus eta look like? What does the distribution of x plus eta look like? Can someone wager a guess? That's very good, yeah. So his response was that x plus eta, the distribution of x plus eta, is going to look like the same damn thing, but now centered at x. What does centered at x mean? Wherever? Wherever 0 is there, I replace that with x. All clear? X can take how many values? So let's just plot both plots. What happens when x is 1? x1 means x0. Okay. Huh? It looks like this. Somebody told me about these Crayola. I want to try these. All good? So what is this plot again? If somebody shows you this plot ever again in your life, what is this plot? No. What is this plot? What is this plot? It is a plot of the probability of x plus eta. Okay. So when people ask you what, they don't want the technical term. They want you to explain what it is semantically. Okay, so this is the probability with which x plus eta occurs when x is plus 1. When x is minus 1, it looks like this. Okay, something like this. So the center here is minus 1, center here is plus 1. Clear? What does my mom know? My mom knows it's either minus 1 or plus 1. She doesn't know what it is. She receives x plus eta. Okay. So now you guys will tell me what she can do with this information. My mom receives x plus eta. She doesn't know what x is. What will she do? She knows this plot and all, okay? She can analyze the peak. She has one value. One sec. She has one value. She doesn't have the distribution. She knows the distribution like on a computer. Okay? She knows it like that the distribution looks like this. But this here is not a graph. This here is one value. Eta is one value. Eta is one value that occurs with a certain probability, and she gets x plus that value of eta. She does not. She receives multiple things, but she does something like this. You will see why she does it at all and why she doesn't directly work with this. Yeah, sorry.
So if she has the plot, she should know the point where both the curves intersect the y.
Fantastic. Okay, where do they intersect? Where do they intersect? Where do you anticipate they intersect?
That point where
At the point at which they intersect.
Yes.
Okay, where do they intersect?
Average of these two values.
Average of which two values?
1 and minus 1. Basically,
What is that value? Thanks. Okay. No, I was asking what this value is. Is it? It's not. It's 1 by root 2 pi is this. Okay, let's get back. So okay, you were saying something about this value. What were you saying?
So if she knows P of 0, I mean the place where the curves intersect the y-axis.
It is 0.
Yes. So at that point, if she gets a positive value more than that value, it has to be plus 1. But if she gets a positive value less than that, it has to be minus 1 because the graph is like that.
Fantastic. So do you get a positive value less than 0? You get a value less than 0. But great answer, by the way. Is this kosher? So let me repeat whatever, sorry I didn't get your name. Whatever Mukund was saying. She knows this. She knows the plot. She knows I'm sending one of these two values. She knows distribution of eta looks like this. Now her desideratum is to find out which of these values I sent. Huh? Now suppose I sent a +1. The value that she is going to receive is going to look like what? Is going with high probability it's going to where be somewhere here between 0 and 1. It will be somewhere here. High probability, right? If I send -1, somewhere here. So then she says, okay, you know what is all this somewhere here? Let me bring together both of these and call that the value 0. Okay? And set that as the threshold, to the left of which I will say that this fellow had -1, this fellow is going to IIT Madras. This, to the right of which this fellow is not going to IIT Madras. Say that again, sorry. So, mine, it's always going to be less than 0. It's going to be less than, so if x is -1, it's going to be less than 0.
What I'm trying to say is, we have, the mother gets a signal x plus 0. Say you are going to IIM, say you are sending a signal -1.
Great point, yeah. Thanks for that. So I came up with that -1, 1 on the fly. Let's think of it as -2, 2. Sorry for that, and great catch, by the way. So all the z values are in -2, 2. Okay. Same thing, whatever I said still holds. Okay. But she can do something much simpler in order to identify what it is that I sent. But I want to make things complicated because real life is complicated. In real life, you don't have these noise values actually being in -2, 2 also. You have this as being in -infinity, infinity. It's just some random thing because these signals interfere however they want. But yeah, great catch, but let us just proceed. Okay, so we have this picture and then my mom is trying to guess -1 or 1 from this picture. And like all of you concurred, a rational thing to do is to guess +1 whenever the value that she gets is larger than 0. So let me say this. So let me call this x hat as the value that my mother guesses my x to be. So x hat again is in -1, 1, but it is her guess of my value. It is not my value itself. So what my mother does is she sets x hat as 1 if y is larger than 0. Whatever you guys said, I'm not doing anything different. And -1 if y is smaller than or equal to 0. Okay. This is what she does. So so I started at 10:20, so I am going to go over time. So let's look at this question again. X is what I had. X is either 1 or -1. X hat is what my mother decodes my x to be. Okay. So this entire thing is what is called a decoder. And I'm just sending the bit, whatever I have across, so I'm not doing any encoding. She is just doing decoding. Okay. So I have x which is either +1 or -1. My mom is decoding x hat which is again either +1 or -1. And the environment between us is trying to play prankster. That's what is going on here. Okay. So let me draw this pictorially. So I have a 1. My mother is decoding either +1 or -1. When will my mother decode +1 if I have transmitted if I have transmitted plus 1. It's just this. Okay. Huh? When y is positive. Y when I transmit 1 is positive. So let's write that. So this link, whatever you see here, is going to happen whenever y when I transmit 1 is positive. Okay. So let's write down the probability of this event. Huh? So what is the chance with which she is going to decode 1 when I have transmitted 1? Can someone take a good guess as to what that is going to look like from this plot? The question is, I want to find the chance or the probability with which my mother decodes my message as 1 when I have really transmitted 1. I have really transmitted 1. My mother is then saying, this fellow must have transmitted 1. Just from this plot, I don't want the value. Let's look at the plot again. So I have transmitted 1. So which plot am I working with? The right side one, red color one. So all probabilities that I compute are with respect to this red color plot. Okay. So now I want to find the probability that my mother decodes me as 1 when I have indeed transmitted a 1. You are saying? Fantastic. So his claim is that it is the probability with which that occurs is the area under this graph that is larger than 0. Area under the red plot larger than 0. Huh? I don't know how much that is. It's just some value. Okay. It depends on what the variance and all is. 70% is just some value you cooked up now. So let's write that. Okay. So let me call it this area. Okay. So that is the probability. What is the probability with which she decodes me as -1 when I have indeed transmitted a 1? Area under the red color plot to the left of 0. This guy. Right? So which link is this? 1 to -1. Can you tell me one curious thing about these two areas? They add up to 1, right? Somewhat intuitive, right? Because you're adding complementary probabilities under the same x value. Let's finish this. I am actually saying no, I am actually saying yes, I am going to IIT Madras. She is hearing it as no. What is that value? Same. Area under the blue curve above 0. Area under the blue plot above 0. Because she needs to decode me as +1, but I need to have truly sent -1. Fantastic. So they are indeed the same value. But let us first identify that it is indeed the other area that we are speaking about, and coincidentally it turns out to be the same value. Okay, it's a consequence. It's not what we started off with. So let me show that anyway here. So it is which area? This area. So it is this area. And likewise the other one, -1 given -1, this one. Okay, all good. So now you have a fairly nuanced understanding of a very basic communications paradigm. So you were saying something about both these probabilities being the same, right? So I don't know what the value is in terms of numbers. So let me just call it some value. Let me call this guy P. Is everyone on board? I'm calling this guy as P. So this is how much? 1 minus P. This is how much? Very good. This is how much? Super. So we have accomplished quite a bit, right? We started from some random electromagnetic signals interfering, this, that. Then we said central limit theorem, we go to Gaussian noise. Then we said, actually, you know what, we don't need to work with Gaussian noise. We can just work with what your mother decodes and what you truly transmit. And that gives you a discrete kind of a plot. Okay. So this is what is called the binary symmetric channel. Okay. So in your in a course on communications, whenever people talk about channel, this is another piece of jargon, they mean a noisy medium. Okay? So channel here means a noisy medium over which you are transmitting or storing information. Okay? So this is similar to the nonsense that led to percolation, the nonsense that led to concentration, and so on. Okay? So percolation, to be very honest, it came from the way coffee percolates in your filter. Okay? Have you seen the working of a filter coffee? How does it work? Huh? Huh. You put a filter, you put coffee powder, then you put rolling boil, okay, always. Rolling boil water, and then it trickles down. But the point is, not all pores allow the water to go through. Right? Some pores say, no, I will not transmit. This is exactly the model that you saw in the first lecture. Some pores just say, no, I am a node, I don't want this coffee particle to go through me. And that is why coffee connoisseurs, they are very fanatical about the kind of filters that they use in particular, so that the coffee percolates the way they want, whatever. Okay? So that's where percolation came from. Concentration came from, okay, we were having this discussion with Abhishek the other day. He said concentration comes from chemical concentration. I said concentration comes from the English concentration, but then we never came to a consensus. So channel here comes from and has remained the same word ever since. So if you guys are old enough, you would have heard of something called the radio. Okay, so the radio is something that used to be there in your car, and you used to press something called a channel, and it will take you to FM 98.3. Okay, it used to be something. So whenever people talk about channel, they mean this, but in particular they mean this. Okay, so how much you know about channels will kind of influence whom you talk to, but then. So I'm going to kind of, so my motivation was to actually talk about coding also, but then I don't have time for that maybe. But let me just give you the term for this. So whatever we saw, the setting where I have a single bit to transmit. I have just one bit, which is either -1 or 1, and I want to transmit that information, right? So that is what is called binary phase shift keying. Okay, binary phase shift keying. It's just jargon, just bear with me. Okay, so this is called BPSK in short. So BPSK signaling, as it is called, whatever you saw here, happens in most communication systems till date because they break the signal up into many of these single bits and then they transmit. So whatever you see in the real world is exactly this, except that I have not spoken to you about how to actually communicate over such a channel. Okay. My mother has a certain probability with which she decodes me. So what is the probability with which she decodes me correctly? So wait, so let's assume that I transmit 1 with probability half, -1 with probability half. Now tell me what is the probability with which my mother. Think. Think, slow. I have a probability distribution on my inputs also. You have heard of law of total probability, chain rule, P of A times P of B given A is P of A times P of A complement times P of. Hey. 11th standard they don't do this stuff. 12th only they do. But you guys have heard of chain rule, but you don't know what I'm saying. Okay, fine. See, once you step out of your 12th, no, you should just unlearn all the jargon that you have learned, so that people come and tell you things like percolation and then you start thinking like that. Okay. So when people they ask you what is this, you should not tell them Gaussian, zero and things like that. Tell them what it is. But okay, where were we? So what is this error probability? B, huh? Why is it 1 minus B? Very good. So I transmit 1 with probability half. Given that I transmit 1, what is the probability that my mother decodes me correctly?
1 minus B.
Next. Why half? I transmit minus 1 with probability half. Same 1 minus P. So 1 minus P is the probability with which she decodes me correctly. So depending on how bad the channel is, this P value can be high. Okay, so if the channel is bad, if the channel is very noisy, then P is very high. What is P here? Remember what P is? What is P? Which area? Orange area, this area. If this area is very large, then I am in big trouble. I need to go to my mother and tell her again whatever I said. If this area is large. Hence, if this area, in other words, if this area is large, P is large, so the probability with which she decodes me correctly is small. Okay? That is one very reasonable goal to do. So one goal, like you said, is to, why are you transmitting minus 1, 1, transmit minus 100 and 100. But then the issue is this. So in real systems, whenever I transmit a signal, I incur energy, right, in energy loss. And when I transmit minus 1, I am incurring 1 unit of energy. When I am transmitting minus 100, I am incurring minus 100 square amount of energy, which is like 10 to the 4 amount of energy. So energy issues are what prevent me from making these as far apart as possible. So to ameliorate this is what brings to light the concept of coding. I am not going to speak about that. So here I was just transmitting minus 1, 1, but then I can transmit minus 1 3 times, right? If I transmit minus 1 3 times, then my mother needs to decode me correctly only once, in some sense, okay? If I transmit minus 1 3 times, what am I transmitting? 1 1 1 essentially. My mother is receiving something. Suppose she receives 0 1 1. So this is something that I also spoke about long time back. So if you do a majority of the received bits, then my mother has a very high chance of decoding whatever it was that I transmitted, so long as I transmit sufficiently many times. Okay? It's what is called the repetition code. Yeah, the hat problem. Yeah.
Again, you will have that same problem of energy loss.
Yes, but the trick is this. The trick is that whenever we talk about energy per unit time. Per unit time means what? Every time I use the channel and send some information, I call that one time instant. So if I am transmitting 3 times minus 1, 1 or minus 1, how many time instants are there? 3, right? What is the total amount of energy that I consume? 3. I divide 3 by 3 and then I say the amount of energy per unit time is still 1 and I am still safe. So energy per unit time is the metric with which such things are measured. I am not going to talk about coding, but you are free to talk to me about it later. But one reason why I wanted to tell you this is that right now the world has moved beyond this communications paradigm. Okay, so many problems in communications are well understood. So we know how to communicate really well. Our 5G, 6G phones work very well. Sorry, 5G phones work very well. And we are just making minor tweaks to the algorithms. We are not making any landmark breakthroughs as yet. So what is hot is what is called quantum error correction. This is a burgeoning field. This is something that you may consider specializing in later on when you actually grow up. It's error correction but quantum. Okay. So the point here is that we are trying to build quantum computers, right? We're trying to build computers based on qubits, whatever that means. And these qubits are very erroneous. The same kind of errors kind of percolate there also. Okay. And now we want to design ways of mitigating noise and errors in those systems. And this field is very nascent. People are still working very hard in order to design good algorithms here. Okay. So this is a field of specialization that you can choose later on.
Thank you, Professor Arvind Rameshwar, for today's informative and interesting session. Your explanation on compression, communication, decoders, noise and communication, the central limit theorem, Gaussian distribution, BPSK, and the binary symmetric channel made the topics very interesting and easy to understand. We truly appreciate your time and guidance, and on behalf of everyone present here, I extend our sincere thanks to you, sir. Thank you.